Hello everyone, let's get started with Calculus Math 2413, Section 4.4. Finally, the fundamental theorem of calculus. We've had some sections of finding the area using the limit definition instead of using the integrals to find definite integrals. Because, much like when we dealt with derivatives, we had to deal with limits to first establish some of the patterns of derivatives. We've now used the limit definition to establish some patterns for integrals. And finally, we're ready to acknowledge and use the shortcuts. Enter the fundamental theorem of calculus, the number one most important. Well, maybe. Derivatives may have an argument, but this, in terms of applications, becomes incredibly important. If a function is continuous on the closed interval a, b, and f is an antiderivative of the function on that interval, then the integral from a to b of the little f of x, our original function, is big F of b minus big F of a. That is, we can take the antiderivative and plug in b and a and subtract them to get the actual value of that definite integral, which is assuredly less work than the limit definition one is. Now you'll notice it says any antiderivative of f, which means we don't really need the plus c, because what happens when you plug in a value and subtract them, whatever constant you attach to the function will get subtracted right off anyway. So below is a little bit of an explanation. As long as you can find an antiderivative of f, you now have a way to evaluate definite integrals without using the limit of a sum. So when applying the fundamental theorem of calculus, the notation below is how we would kind of organize it. The integral of from a to b of f of x dx gives you at big F of x, our antiderivative, and the way we'll write this is evaluated from a to b, which is a fancy way of saying you plug in b, and then you subtract plugging in a, and that gives you your value. So as an example, to evaluate the integral from 1 to 3 of x cubed dx, we have the integral from 1 to 3 of x cubed dx. Well, the antiderivative of x cubed is x to the fourth over 4, evaluated from 1 to 3, which means we have 3 to the fourth over 4 minus 1 to the fourth over 4, which is 81 over 4 minus 1/4, which is 80 over 4, which reduces to 20. And again, even though we could toss on the plus c, what you recognize is if you subtract, that plus c gets subtracted off anyway. So there's no reason to do any more than just taking the basic function, because any constant on a definite integral will go away. However, if you're still doing indefinite integrals, you still would like your plus c to represent that family. So let's do some quick examples. The integral from 1 to 2 of x squared minus 3 dx. So we need to find an antiderivative of x squared minus 3. For x squared, that would be x cubed divided by our new power, 3. For the minus 3, to integrate that, really our x is to the 0 power right now, so anytime you have a constant, it's minus 3x. And this will be evaluated from 1 to 2. So if I plug in 2, that's 2 cubed over 3 minus 3 times 2, minus, plugging in 1 cubed over 3 minus 3 times 1. Make sure to distribute your powers as needed. This is 8/3 minus 6 minus 1/3 plus 3. 8/3 minus 1/3 is 7/3. Negative 6 plus 3 is minus 3, so this is negative 2/3. Now, we can continue the integral from 1 to 4 of 3 times the square root of x. It's usually easier for us if we go the integral of 1 to 4 of 3x to the 1/2 power dx. The integral here, add 1 to the power, so that would be x to the 3/2. divided by 3 halves. So that would be 3x to the 3 halves over 3 halves, which really times 2/3. So it ends up being 2x to the 3 halves evaluated from 1 to 4. Now notice that when you do integrate this, even though we talked about this a little bit with the indefinite integrals, is your dx does go away, your variable of integration. You've done the integration, so now it's gone. Now, that means this is 2 times 4 to the 3 halves minus 2 times 1 to the 3 halves. 4 to the 3 halves is 8. 1 to the 3 halves is 1. That's 16 minus 2, which is 14. And we can even do this with trig functions, which is nice for us. The integral from 0 to pi over 4 of secant squared x dx. The integral of secant squared x will be tangent x evaluated from 0 to 4, or pi over 4. So that's the tangent of pi over 4 minus the tangent of 0, which is 1, minus 0, which is 1. So look how quickly we just did 3 problems, and most likely if we were still using the limit definition version, we'd still be doing the first one. Now, if that means it's a big game changer, and that means some of your other calculus theorems are starting to be applied to integrals. One of them is the mean value theorem for integrals. That is, if f is continuous on the closed interval, there exists a number c such that the integral from a to b of f of x dx equals f of c times b minus a. Basically, they're saying if you have a curve at this area under the curve, there exists some value c such that f of c creates a rectangle of exactly the same size area that's under the curve. Maybe not super important, but it does exist. And the value of f of c given in the mean value theorem for integrals is called the average value of f on the interval, because if you have the average value, it creates an equivalent size to the area. Now, if you wanted to find what that value was, to find the average value over an integral, you take the total area under the integral and divide it by the width of the integral, which in our case would be b minus a. So naturally, that means the average value of the function on the interval is 1 over b minus a times the integral of your function. So what does that look like in a problem? Find the average value on the function f of x equals 3x squared minus 2x on the interval 1, 4. Well, this is our a and b. b minus a is 4 minus 1, which is 3. So that means to find the average value, take 1/3 times the integral from 1 to 4 of 3x squared minus 2x dx. So we've got 1/3. The integral here should be x cubed minus x squared evaluated from 1 to 4, which means it's 1/3 times 4 cubed minus 4 squared minus 1/3 times 1 cubed minus 1 squared. So that's 1/3 times, this is 64 minus 16 minus 1/3 of 1 minus 1. Since this is 0, this will just be 1/3 times 64 minus 16, which is 1/3 of 48, which is 16. So we're basically saying the average value of this function is 16 across the interval 1 to 4. Now, does that kind of make sense? If we plug in 1 here, we get a value of 1. If we get them to plug in a value of 4 here, we get 48 minus 8, which is 40. So it stands to reason that our answer should be somewhere between the two of those. Now, why is it not exactly right between 1 and 40? Because our function looks kind of like this. And so it's slowly increasing, so it would be closer to the lower end. So this is just an example, and we'll continue talking about other things that now apply in the next video.